Tonight, let us begin with something very small and very familiar. A glass of water resting beside the bed. It catches a little light. It makes no argument about geology. It simply waits there in the ordinary way water always has, in cups and clouds and kettles and rain gutters, in rivers, under bridges and ice, pressed into the backs of mountains. When most of us picture the water of Earth, we picture the parts that move and shine. We picture coastlines, fog, storms, lakes, wet soil, and the careful dripping of a tap that was not tightened quite enough. It is a reasonable picture. The planet does seem to keep its water where we can notice it. The oceans spread across the surface in a thin, restless skin. Ice gathers at the poles and on high ground. Water vapor wanders the air. Groundwater tucks itself into pores and cracks not terribly far below our feet. Even when water hides, it usually hides in ways we already understand. It seeps, it pools, it phrases, it flows. And then there is the stranger claim, the one that appears every so often with the startled energy of a rumor overheard on a train. There is an ocean hidden inside Earth. That sentence sounds as if our planet might contain some impossible secret bay. A dark inland sea under the crust, waiting for a ship that will never arrive. But that is not the story. There is no navigable cavern, no buried surf breaking against stone walls, no great free reservoir where whales have taken up a private subterranean life. The true story is quieter than that, and much stranger, far below the familiar weather and tides, hundreds of kilometers down. Earth enters conditions so severe that ordinary liquid water cannot simply sit there as a normal sea. The pressure is immense. The rock is hot. The world becomes less like a cave and more like a slow mechanical interior. Dense and glowing in the mind even when dark in reality. And yet, in this deep region, scientists have found reason to think that very large amounts of water may still be present, not as open liquid, but bound into the minerals of the mantle itself. This is the crucial turn in the story. When geologists talk about hidden water inside Earth, they often do not mean droplets in empty space. They mean water reduced to a chemical presence inside solid rock. Sometimes that presence is described as hydroxyl, where hydrogen and oxygen are incorporated into a mineral structure. Sometimes hydrogen is tucked into tiny imperfections in a crystal lattice, small substitutions and misfits inside an orderly pattern. The rock remains rock. It does not slosh, it does not splash, and yet it carries one of the ingredients of water as part of what it is. At first, this can feel like a trick of language. If the water is not liquid, is it really water in any meaningful sense? The answer is yes, though not in the way a glass beside the bed is water. A wooden violin contains music only in potential, but the potential matters. In something similar, deep minerals can contain water not as a pool, but as a capacity, a stored chemical fact that changes how the planet behaves. The scale is what makes this so remarkable. The ocean we know is vast to us because we live on its shore and cross it with ships and imagine its depths as nearly endless. But on a planetary scale, the surface ocean is a very thin layer. If Earth were simplified in the mind to a large dark sphere, the familiar water above would resemble a delicate wash of color on the outside, impressive to those standing near it, but slight compared with the enormous volume of rock below. Now imagine taking just a faint trace of blue and dispersing it through a vast woven blanket. Each thread holds almost nothing on its own. You would never point to one strand and say, "There is the blue," but spread that color through the entire blanket, and suddenly the total amount becomes substantial. That is the deep water idea in one gentle picture. A little capacity inside a great deal of rock can add up to an astonishing planetary reservoir. This is why the claim about a hidden ocean refuses to disappear. It is not accurate in the dramatic way rumors prefer, but it gestures toward a real and profound possibility. The mantle occupies such an enormous share of Earth's volume that even minerals holding modest amounts of water by percentage, but collectively store quantities that matter on the scale of oceans, continents, volcanoes, and very long stretches of planetary time. So the hidden ocean is not a place. It is not somewhere you could drain, dive into, or map with a coastline. It is better understood as a property of deep earth, a way rock can carry water invisibly within itself. The planet, in other words, may be wetter than it looks, but wet in a disciplined, mineral, high-pressure way that has almost nothing to do with underground seas from old adventure novels. And that difference matters, because once water becomes part of stone, it begins to influence stone. It can alter melting temperatures. It can change how minerals behave. It can travel downward with sinking slabs of crust and return upward again through heat and melting and volcanism. The familiar water cycle of clouds and rain may have a much deeper companion, moving not over days or seasons, but across millions of years through the interior of the planet. For now, though, we can rest with the first quiet correction. The water beneath the water is real, but it is not waiting in some vast hidden chamber. It is distributed, locked, carried, and transformed. It lives inside the grammar of minerals, and to understand how an apparently dry stone can hold the ingredients of seas, we have to look more closely at what a crystal is willing to admit. If we move closer now, away from the grand cutaway of the whole planet, the strange story becomes smaller and somehow more peculiar. Instead of staring at continents and trenches, we pause before a single grain of mantle mineral, turning slowly in the dark. To the eye or to the hand, it would seem dry beyond argument. It is hard, solid, finished. The ordinary expectation is simple enough. A crystal should be a neat arrangement of atoms, tightly fitted together, with no room for something as familiar and restless as water. But crystals are not little statues. They are orderly, yes, though not perfectly so. Their atoms settle into repeating patterns, more like disciplined neighborhoods than flawless monuments. And inside those neighborhoods, a few addresses are missing. An atom that ought to be present may be absent. One chemical guest may take the place of another. Tiny imbalances appear, then are compensated for elsewhere. At the human scale, the mineral still looks complete. At the atomic scale, it contains a scattering of opportunities. This is where the story turns. Deep inside certain minerals, hydrogen can enter those imperfect arrangements and become part of the structure itself, usually as hydroxyl, a pairing of oxygen and hydrogen. That is not the same thing as droplets hiding in a crack. It is not a secret puddle. It is chemistry taking up residence inside the architecture of stone. It helps to separate three ideas that are often blurred together. First, there is a pore, an open space, the sort of gap that can hold fluid the way a sponge holds water. A sponge feels wet because liquid sits in connected voids that could be squeezed, drained, or soaked up again. That is the familiar household version of water storage. Second, there is an inclusion, which is more like a tiny sealed bubble trapped during growth. Quartz can contain minute pockets of fluid, little capsules enclosed by crystal. They are real and important, but they remain pockets. The water there is still a fluid, simply imprisoned on a very small scale. And then there is the third category, which matters most for the deep earth. In minerals such as olivine, which dominates much of the upper mantle, water may be present even when no pore and no fluid pocket can be found. Hydrogen is bound into the crystal structure. The mineral can be called nominally anhydrous, meaning it is not a water mineral in the obvious sense, and yet it may still host measurable amounts of hydroxyl tucked into structural irregularities. Dry-looking rock, in other words, can carry water without feeling remotely wet. One way to picture this is as a vast hotel whose rooms are mostly occupied. The building is orderly. The corridors repeat. Most doors lead exactly where the blueprint says they should, but scattered across many floors are a few vacancies, a few substitutions, a few awkward arrangements where the plan has been adjusted. Tiny guests can be accommodated in those scattered spaces, not by flooding the lobby, but by fitting discreetly into the building's internal logic. No single room seems important. Across an immense number of crystals, the lodging adds up. Pressure matters here, and so does chemistry. Deep in the earth, atoms are not choosing positions under calm laboratory conditions. They are under immense compression and high temperature, forced into arrangements that can change with depth. A mineral that is stable nearer the surface may become unstable farther down. Another form may replace it, with a different structure and a different ability to host hydrogen. The capacity of rock to hold water is therefore not fixed once and for all. It depends on which minerals are present, how their lattices are arranged, and what the surrounding pressure allows. This is one reason the viral idea of an ocean hidden underground misses the real wonder. A liquid ocean is easy to imagine because we already know what an ocean looks like. A mantle mineral quietly accepting hydroxyl into atomic defects is harder to picture, but much stranger once it comes into focus. It means the deep earth can participate in a water cycle without underground waves, without open caverns, and without anything resembling a submerged chamber waiting in the dark. The consequence is gentle but enormous. A rock can look dull, dense, and uneventful while still carrying one of the most important ingredients in planetary history. Water does not have to slosh to travel. It can ride inward as part of minerals, held in structures too small to see, surviving journeys through heat and pressure until later changes release it again. So the lesson of this rotating grain is a modest one, though it rearranges the whole problem. Dryness to the hand says very little about a crystal's interior life. What seems closed may contain small accommodations. What seems finished may still admit a wandering hydrogen. And if that is true, then the deep earth is not merely hot rock beneath water, but rock with its own quiet way of keeping water close. In the next step downward, that quiet arrangement will not remain the same. As pressure increases, the hotel is rebuilt floor by floor, and the crystal enters forms that belong to deeper rooms of the planet. If we follow one small grain farther down, past the crust and into the long dark body of the mantle, the first surprise is how undramatic the change appears. There is no great underground surf, no warm black chamber with tides rolling through it. The rock below is hotter, certainly, and heavier with every kilometer, but most of it remains solid. It yields the way wax yields in a slow summer window, or the way glacier ice moves while still looking firm beneath your boots. The deep earth is not a furnace full of liquid stone. It is a crowded interior that deforms patiently under pressure. This is one of those scientific corrections that sounds less exciting at first and then becomes much stranger once it settles in. We are used to thinking that heat melts things and that deeper means more molten. Yet in the mantle, pressure keeps matter disciplined. Atoms are pushed so closely together that many minerals hold their shape even at temperatures that would seem outrageous at the surface. Over immense spans of time, solid rock can still circulate. It can rise, sink, fold, and creep. The mantle flows, but it does so with the dignity of a substance in no hurry. That slow movement is part of mantle convection, the deep planetary churning that helps carry heat outward from Earth's interior. Warm material tends to become buoyant and drift upward. Cooler, denser material tends to sink, not quickly enough for any human eye to witness directly, but steadily enough to reorganize the planet over millions of years. Continents ride above this patient motion. Ocean floors are created and recycled by it, and water, once carried down from the surface, must travel through a world that is neither rigid in the everyday sense nor liquid in the familiar one. As the grain descends, another quiet drama begins. The mineral itself must adapt. Near the upper mantle, a great deal of the rock is rich in olivine, a mineral so common that much of the mantle can be described through its behavior, but olivine does not keep the same arrangement forever. At greater depths, the pressure becomes too insistent for its original structure. The atoms are still made of the same ingredients, but they are asked to stand in a different pattern. An ordinary room offers a useful image. Imagine dancers spread comfortably across a hall, each with enough space to turn. Then the walls begin to move inward. The dancers are not replaced. No one exits, but the formation must tighten. Arms tuck closer. Lines become denser. The group discovers a new geometry simply because the room no longer allows the old one. Something like this happens to olivine as it approaches about 410 kilometers below the surface. Under increasing pressure, it transforms into a denser structure called wadsleyite. Deeper still, within the same broad interval, it becomes ringwoodite, denser again, the same basic chemistry reorganized for a more crowded world. By the time the grain approaches about 660 kilometers depth, those structures give way to minerals stable in the lower mantle, where the rules of packing change once more. These transitions matter for several reasons at once. They influence how seismic waves travel, which is how geophysicists learned that the mantle is not one bland, uninterrupted mass. When earthquake waves pass through Earth, they speed up, slow down, bend, and reflect depending on the materials they encounter. Around 410 kilometers and 660 kilometers depth, those waves behave as though they have crossed real boundaries. Not empty gaps, not caverns, but changes in mineral architecture. Deep inside the planet, two invisible thresholds mark where one set of crystalline arrangements gives way to another. Between those thresholds lies the mantle transition zone, a region that turns out to be unusually important for our story. Because these rearranged minerals do not all welcome hydrogen in the same way, The deep Earth's ability to store water changes with structure. A little hydroxyl can fit into one mineral more readily than another. The same ingredients, under different pressure, create different lodging for hydrogen. And once enough grains across enough rock are involved, a tiny difference in what each crystal can host becomes a planetary scale consequence. This is why the mantle cannot be treated as a single anonymous block of hot stone. Its architecture changes with depth, and those changes shape what the planet can keep, what it releases, and what it carries farther down. The transition zone is not notable because it contains a dramatic underground sea. It is notable because solid minerals there may be especially good at holding chemically bound water. The room narrows, the dancers change formation, and suddenly the planet acquires a new kind of storage. There is something almost bureaucratic about it. The deep Earth keeps no shining reservoir with a clear shoreline. It keeps a ledger written into structure. A mineral in one arrangement may admit only a little hydrogen. The same material, pressed into a tighter form, may admit more. Then, deeper still, another rearrangement may reduce that welcome again. Water, in this sense, is not merely carried downward. It is negotiated, accepted, refused, transferred, and passed along according to the local rules of crystal stability. So Chapter 3 leaves us standing between two seismic lines, one near 410 kilometers, one near 660, looking not at an abyss, but at a hidden interval with unusual habits. Its roof and floor are drawn by pressure itself. Its walls are made of changing atomic order, and inside that interval, one mineral in particular has become famous for wearing an improbable shade of blue, and for hinting that the deep Earth may be far wetter, in a bound and disciplined way, than the surface once imagined. In the next chapter, we meet that mineral directly. By the time our borrowed water has traveled down into the transition zone, the scenery has become almost impolite to the imagination. The pressures are so large, the temperatures so high, that ordinary categories begin to lose their grip. Rock is still rock, and yet it behaves with a kind of deep patience that does not resemble the stone in a garden wall. It changes structure. It takes on new arrangements. And in this dim interval inside the planet, one mineral has become unexpectedly famous for its ability to keep a secret. Its name is ringwoodite, which sounds a little like the name of a village one passes through without stopping. In fact, it was first recognized in the laboratory and later identified in nature, and that origin might make it seem like a technical curiosity, the sort of thing appreciated mainly by people who enjoy phase diagrams and high-pressure apparatus. You might imagine a rare blue grain in a drawer, labeled carefully, interesting but remote from the life of oceans and rain. Instead, ringwoodite turns out to sit very near the center of the hidden water story. This is because the transition zone, hundreds of kilometers below the surface, contains minerals arranged for those particular conditions of pressure and heat, and ringwoodite is one of the important forms there. Under such conditions, its structure can host hydrogen and oxygen not as little droplets and not as open pockets of liquid, but as hydroxyl bound into the mineral itself. The distinction matters. This is not free water waiting in caverns. It is chemistry folded into crystal structure, held in place by the same strict order that holds the mineral together at all. If that sounds modest, almost fussy, it helps to look at the scale from the other direction. A single crystal can hold only a limited amount. No one grain is dramatic. The oddness appears when that modest capacity is repeated again and again through a vast region of the planet. Then a small percentage becomes an enormous quantity. The trace, when multiplied by enough world, stops being a trace. That is why ringwoodite has such a calm and slightly unnerving importance. In laboratory studies, hydrous ringwoodite has been made and measured, and it can contain a meaningful fraction of water by weight under the right deep mantle conditions. Not 50%, not some fantasy of stone turning into soup, but enough that geophysicists must take the number seriously, enough that the transition zone becomes not merely a passage between upper and lower mantle, but a potential reservoir whose significance comes from chemistry meeting volume. It is a little like discovering that a certain kind of apartment wall contains a built-in cupboard so small you would ignore it in one room, then realizing the same design has been repeated across every building in a city. The city does not look different from the street. There are no overflowing closets in public view. Yet the total storage changes your understanding of the place. Ringwoodite invites a similar correction. The hidden water is not gathered into one dramatic chamber. It is distributed. It is structural. It is dispersed through billions upon billions of locked blue rooms scattered through a continent of stone. Each room is tiny. The architecture is everything. This is where the most spectacular claims have to be handled with some care. Because ringwoodite can hold a significant amount of hydroxyl, and because the transition zone occupies such a large volume, the total storage capacity can add up to something comparable to the water at the surface. That is the headline people tend to remember. But capacity is not the same thing as inventory. A pantry may have shelves enough for a year of food and still be half empty. The mineral can host water without proving that every suitable crystal does so to the maximum possible extent. Scientists are careful here for good reason. The deep earth is not uniform. Temperature varies. Composition varies. Material is moving slowly over geological time. Some regions may be relatively rich in bound water, others much drier. Some water continues downward in changing minerals. Some helps trigger melting as pressure and structure shift. Some eventually returns upward through volcanism. So when researchers speak about how much water the transition zone might store, they are usually describing a plausible range, not a single final total engraved on a brass plaque. Still, even uncertainty has shape. The reason ringwoodite matters is not that it guarantees one exact number. It matters because it makes large, deep storage physically reasonable. It turns a wild-sounding claim into a chemically respectable one. Once you know that hydroxyl can be housed inside this mineral under transition zone conditions, the deep planet stops seeming dry by definition. It becomes a place where water can be hidden in plain mineralogical sight. There is also something quietly pleasing about the color. Ringwoodite is often described as blue, and although the blueness is not the scientific point, it feels almost too fitting. Down in darkness, under pressures no human body could meet, the story resolves around a blue crystal carrying the signature of water without ever becoming a pool. It is not the ocean in miniature. It is something stranger, a keeper of ingredients, a disciplined host, a mineral that stores part of the planet's wetness in a form that looks, from our ordinary surface perspective, almost impossible. And if the hidden ocean idea has lingered because it sounds grand, ringwoodite offers a better kind of grandeur. Not a single astonishing chamber, but a distributed system. Not a mythic abyss full of sloshing water, but a deep ledger written in chemistry and scale. The wonder comes from restraint. A little water here, a little there, held for immense spans of time, adds up because Earth is so large and so patient. For a while, much of this argument lived most comfortably in experiments, equations, and careful inference. Researchers could grow hydrous ringwoodite, test its properties, and show that the mineral was capable of playing this role. That was already enough to shift the conversation. But laboratory confidence always becomes more satisfying when the planet itself offers a specimen. And eventually, from Brazil, it did. If the deep Earth ever sends a letter to the surface, it does not choose elegant stationery. It arrives in upheaval, inside a rock blasted upward at astonishing speed, through a volcanic pipe that opens briefly and then goes quiet again. Out of that rough journey may come something that, in a jewelry store, sits beneath careful lights and velvet. A diamond looks almost too self-contained to tell a story, and yet some of the most useful diamonds are not the flawless ones. They are stones with tiny flaws and trapped specks inside them, the ones a gem seller might find less enchanting. To a geologist, those imperfections can be more generous than the sparkle. They can reveal where a diamond formed, what surrounded it, and what the deep planet was doing before the stone was flung toward daylight. We usually think diamonds tell us about carbon, pressure, luxury, or patience. We do not expect them to comment on water, certainly not on the hidden water budget of the mantle, hundreds of kilometers below our feet. A diamond seems like the wrong witness for that kind of testimony. But diamonds have one remarkable habit. When they grow around a grain of some other mineral, they conceal it away and carry it upward like a sample, locked inside an almost unbreakable bottle. That matters because the deep Earth is not a place we can visit directly. The rocks we would most like to inspect do not sit waiting in a neat outcrop. They are transformed, reheated, squeezed, and often altered on their way upward. By the time a deep mineral reaches the surface, it may no longer be the same mineral at all. Pressure falls, temperature changes, crystal structures rearrange themselves. The evidence edits itself while we are trying to read it. A diamond can interrupt that editing. If a mineral grain becomes trapped inside one while both are still deep in the mantle, the diamond acts as a tiny pressure vessel. It does not preserve everything perfectly, but it gives the inclusion a better chance of surviving the trip with some of its original identity intact. It is a hard, stubborn capsule made by the planet for its own reasons, and only accidentally useful to science. This is why certain diamonds from Juana, in western Brazil, became so important. That region is known for so-called superdeep diamonds, stones thought to have formed far below the depths of most gem diamonds. They are fragments of a difficult conversation between the surface and the interior. In 2014, one of these Brazilian diamonds yielded a microscopic inclusion that drew extraordinary attention: ringwoodite. Ringwoodite is not a household mineral name, which is probably just as well. But deep inside Earth, ringwoodite matters a great deal. It is a high-pressure form related to olivine, stable in the mantle transition zone, roughly between 410 and 660 kilometers down. Earlier chapters have already brought us to that region, and to the idea that minerals there can hold hydrogen in their structures as hydroxyl. What had been missing was a natural sample from that depth range that clearly showed the point outside the laboratory. The tiny inclusion in the Juana diamond helped supply that missing piece. Researchers studied it carefully, because nothing about such a claim could be casual. The grain was minute, and the stakes were large. If it really was ringwoodite, and if that ringwoodite really contained hydroxyl, then a nearly invisible speck would offer direct evidence that at least part of the transition zone is hydrous. To reach that conclusion, scientists did not simply hold the diamond to the light and make a guess. They reconstructed pressure histories, examined the chemistry of the inclusion, and used spectroscopic methods to identify the signatures associated with hydroxyl in the mineral. Spectroscopy listens to how matter interacts with light. Certain bonds absorb energy in characteristic ways, leaving behind a pattern delicate but readable if the sample is treated with enough care. So the argument came together piece by piece. The inclusion's identity matched ringwoodite. Its context fit a deep origin. Its spectral features indicated hydroxyl bound within the mineral, not liquid water sloshing in a pocket, not a melt pretending to be a crystal, not contamination from the journey near the surface. A hydrous mineral inclusion preserved inside diamond, carried from the transition zone to the world above. This did not mean the whole transition zone had been fully inventoried, or that every part of it contained the same amount of water, or that one mineral grain had solved the planetary ledger. But the finding mattered precisely because it was so modest in size and so difficult to dismiss. Grand claims about hidden oceans can sound airy and theatrical. A microscopic inclusion inside a battered diamond is the opposite. It is stubborn evidence. There is something almost funny about the scale of it. A person could lose such a stone in the lining of a coat and never know. Yet inside it sat a clue about a region of Earth so vast that maps begin to feel ceremonial. The message was small because that is often how geology speaks most clearly, with trapped grains, pressure scars, altered rims, and faint absorptions in a spectrum. The transition zone had long been suspected as a possible reservoir for deep water, but here at last was a natural sample pointing in that direction from the inside. A diamond no wider than a few millimeters had arrived carrying proof that the mantle below our ordinary world is not uniformly dry stone. Somewhere in that dark interval, water had entered mineral structure and stayed there under immense pressure, waiting to be noticed. So the diamond's message was not dramatic, but it was profound. The hidden reservoir was becoming less hypothetical, less dependent on experiments alone, more anchored to objects the planet had delivered. A sealed bottle had washed ashore from the deep mantle, and when scientists uncorked it with light and patience, the note inside said, "Yes, water lives here too." And once one diamond had spoken so clearly, it became easier to listen for others. More stones, more inclusions, more fragments of the deep interior would begin to suggest that the story was real, but not simple. The mantle was not giving up a single secret. It was releasing a scattered archive. By this point in our descent, water has already learned some unusual manners. It has stopped behaving like the familiar liquid in a glass. It has taken shelter inside minerals, ridden downward in dark stone, and become part of the slow interior traffic of the planet. There is another, even stranger possibility waiting inside a diamond. Not a pool, not a hidden cavern, just a tiny inclusion so small it could disappear under a thumbnail, carrying evidence that water can wear a costume almost no one on the surface ever meets. If we hear the word ice, most of us picture a simple domestic thing: a cube in a drink, frost on a window, snow packed into the edge of a boot. Ice belongs to cold places and ordinary pressures. The deep mantle offers neither. It is hot, compressed, and severe, so it seems almost impolite to suggest that a form of ice might exist there at all, much less survive a journey toward the surface inside a gemstone born under crushing conditions. And yet water is less loyal to our everyday expectations than we might like. Change the pressure enough, and it reorganizes itself into unfamiliar forms. At the surface, we mostly know the version called ice eye, the open, hexagonal structure that makes snowflakes and floating ice cubes. But water has a whole wardrobe of phases. Some appear under carefully chilled laboratory conditions. Others require pressures so large that the molecules pack together more tightly, abandoning the airy architecture of winter. One of these forms is called Ice Roman 7, and it belongs to a world far deeper than any freezer. Ice Roman 7 does not look romantic. It is not the lacework of a pond in January. It is a dense, high-pressure arrangement, stable under conditions that would make ordinary ice impossible. In laboratories, physicists can produce it by squeezing water with diamond anvil cells, tiny devices that press samples between diamond tips until the pressure begins to resemble parts of the deep earth. Out there in the mantle, no one expects little glittering snowbanks. But under the right conditions, water-rich material can exist in forms that include this compressed phase, and that is where the diamond inclusion becomes so compelling. Imagine turning a diamond under faint light and noticing that the jewel is not perfectly pure. Inside is a minute-trapped pocket, sealed away during the diamond's formation and later carried upward. Such inclusions are awkward, precious witnesses. They do not speak clearly. They have been squeezed, heated, transported, and decompressed over immense spans of time. They may have changed on the way. They may preserve only part of the original story. Still, when researchers examine some deep origin diamonds and identify Ice Roman 7 in their inclusions, the result is hard to ignore. It suggests that, at great depth, water-rich fluid was present locally enough to become trapped. That last phrase matters. Water-rich fluid is not the same as a global underground ocean. It does not mean a vast hidden chamber sloshing beneath our feet. It means that in particular places, under particular conditions, mobile fluid existed deep in the mantle and left behind a mineralogical clue. This is a quieter claim than the viral version, and much more interesting. The deep earth is not only storing hydrogen in mineral structures. In some regions, it also seems capable of hosting pockets of fluid that move, react, and briefly become part of the chemistry of a living planet. The caution here is part of the beauty. A diamond inclusion is not a perfect, untouched bottle. As a diamond rises, the pressure around the inclusion changes dramatically. Water can pass through phase changes during that ascent. A trapped fluid may freeze into Ice Roman 7 at one stage, transform again at another, or preserve a mixed and partial record of what happened. Scientists have to ask an unglamorous but essential question. Are we seeing the original deep condition, or a later overprint written during decompression? The answer is rarely simple. The inclusion is less like a photograph than a note that has been folded, dampened, and carried in a pocket for a very long journey. Even so, these notes are extraordinary. They tell us that water does not merely hide by dissolving itself into the crystal habits of mantle minerals. Sometimes it gathers more locally. Sometimes it becomes fluid enough to travel short distances, interact with surrounding rock, and then leave behind a trace inside one of the hardest substances we know, a snowflake's distant cousin, locked inside a furnace-born jewel. Sounds like the sort of idea a storyteller would invent after midnight. But the actual science is calmer and stranger. Pressure can make water into a phase that belongs naturally to depths we cannot visit. This matters because mobility changes everything. Structurally bound hydroxyl can ride inside minerals for enormous stretches of time. A fluid, even a local one, can move differently, transport materials differently, and help trigger different reactions. It can alter how rocks melt, how elements travel, and how the deep water cycle shifts between quiet storage and slow release. The mantle is not one uniform dampness. It is a place where water changes roll from region to region, sometimes hidden in crystal structure, sometimes gathered into fluids, always answering to pressure. So the lesson of Ice Romans 7 is not that the deep earth contains a secret frozen sea. It is that water changes costume as the planet changes the stage. Under one set of conditions, it is bound into minerals. Under another, it becomes a dense fluid. Under another, it crystallizes into a form of ice that would seem absurd anywhere near a kitchen sink. The farther down we go, the less useful our ordinary intuitions become, and because no drill can descend to these depths and watch the costume changes in person, scientists have learned to build tiny versions of the mantle on a laboratory table, squeezing and heating small samples until deep earth water reveals for a moment how it behaves. After the quiet authority of a natural diamond, it is almost charming to arrive at a laboratory bench. The mantle, which seems to belong only to abyssal depths and impossible distances, now appears beside screws, polished metal, lenses, and a sample so small it can barely justify the word object. The ordinary expectation is that the deep earth must remain mostly a matter of inference. We listen to earthquakes. We write equations. We make careful guesses about a realm no hand can visit. And that is true. Then comes the odd turn. To study a place hundreds of kilometers down, researchers sometimes rebuild a tiny portion of it on a tabletop and watch what happens. The most elegant tool for this is the diamond cell. Its principle is simple enough to sound almost mischievous. Take two diamonds with very small flat tips, place a microscopic sample between them, press. Because the contact area is so tiny, the pressure rises enormously. With enough care, those two transparent points can squeeze matter into conditions like those found deep within the earth. Not the whole planet, of course, only a minute chamber, but that chamber can become a faithful little room of the mantle. The sample may be thinner than a human hair, tucked into a metal gasket with a hole at its center. Sometimes a pressure marker is added, or a carefully chosen mixture of starting materials meant to imitate a mineral assemblage from the transition zone. Under a microscope, the setup looks less like geology than watchmaking. The ambition is enormous. A grain almost too small to see is being asked to stand in for a deep planetary environment. Pressure alone is not enough. The mantle is not merely crushed, it is also hot, and not in the way an oven is hot. To imitate those conditions, researchers might use lasers aimed through the diamonds themselves. The diamonds press and the lasers heat. The sample glows. Temperatures climb high enough for atoms to rearrange their loyalties. A mineral stable at one depth may become unstable at another. Hydrogen may remain bound in one structure, then begin to leave as the structure changes. In these experiments, The invisible habits of the deep earth are coaxed into happening on command. There is another family of instruments as well, less jewel-like and more architectural, multi-anvil presses. They use staged sets of anvils that converge inward, compressing a somewhat larger sample volume. Larger is a relative word here. It still means small by everyday standards, but it could be large enough to produce material for later analysis, enough to recover a synthetic mineral and ask, whence it returns from extreme conditions, what exactly it became. That matters because a high-pressure experiment is not only about creating conditions, it is also about seeing clearly while those conditions exist. So laboratories pair pressure devices with methods of observation. Spectroscopy can reveal how atoms are bonded and whether hydroxyl remains tucked into a crystal structure. X-ray diffraction can show how the lattice itself is arranged, because the pattern of scattered X-rays changes with the geometry of the crystal. At synchrotron facilities, where X-ray beams are exceptionally bright and precise, researchers can watch a sample change while it is still under pressure and heat. Instead of waiting for the experiment to end and hoping the evidence survived the trip back, they can observe the transformation as it happens. This is especially useful for a mineral such as ringwoodite, whose significance depends not on appearance but on behavior. In the deep transition zone, ringwoodite can host hydroxyl in its structure. The question is not simply whether ringwoodite can exist, but under what pressures and temperatures it forms, how much water it can retain, and when it begins to release that water as conditions shift. So researchers synthesize hydrous ringwoodite in the lab and then edge its experimental window open or closed. They heat it. They compress it further. They let it react into other phases. In effect, they ask the mineral to confess the terms of its stability. When water is released, the result is not a theatrical gush. It may emerge as melt, as fluid, or as a redistribution of hydrogen during transformation, depending on the exact experiment and the chemical system involved. The changes are delicate, but their implications are large. If a hydrous mineral breaks down at a particular depth range, that tells us where water may be transferred from one kind of storage to another inside the earth. It tells us where rock may weaken, where melting may begin more easily, and where seismic or electrical properties might shift in ways instruments can detect from far away. This is why experimental calibration matters so much. A single laboratory result is not the planet. Real mantle rocks are chemically messy and stirred by motion no apparatus can fully reproduce. So researchers repeat experiments, compare devices, adjust pressure scales, and check whether one method agrees with another. The work has a patient quality. It is less like announcing a revelation than tuning a difficult instrument, until several lines of evidence begin to harmonize, and when they do, the reward is subtle and profound. A seismic anomaly is no longer just an abstract patch on a model. An electrically conductive region is no longer merely a colored zone on a cross-section. Experimental mineral physics gives those distant signals something like texture. It tells us which deep materials might plausibly create them and under what conditions. The laboratory does not replace the planet. It teaches us how to read the planet more honestly. Then there is something quietly moving in that. On a bench top between two small diamonds, a fragment of the deep earth is asked to rehearse its part. The sample is microscopic. The pressures are immense. The conclusions are careful, yet from this tiny chamber comes a bridge between chemistry in a crystal and patterns that stretch beneath oceans and continents. A room of the mantle, rebuilt inside the eye of a needle, helps explain a world no one can touch. Even these miniature rehearsals are only part of the story. If experiments teach us what deep minerals can do, the next clues show us what the whole planet is doing in motion, as waves pass through it and return with news from the dark. The deeper this story goes, the less the planet can be inspected with eyes. There comes a point where even a diamond, even a tiny grain rescued from a volcano, is no longer enough on its own. So the laboratory grows dim for a moment, and we listen instead. Somewhere on Earth, rock breaks along a fault. The movement is brief, but the planet keeps repeating it for us, sending the vibration outward through crust and mantle and into instruments waiting on the surface. At first, this seems almost unfairly indirect. If you want to know whether the deep mantle contains water, you might hope for a sample bottle or at least a clearer label. Seismic waves offer neither. They arrive as timings, strengths, absences, small delays, faint blurring. Traditionally, they are best known for showing boundaries, the way an echo can tell you where a room begins and ends. They can reveal that one layer gives way to another, or that a body of rock is unusually fast or unusually slow at carrying a pulse. It is easy to imagine they tell us mostly about shape and density, the broad architecture of the interior. But water, even when it is not present as liquid, can change the way deep rock behaves. It can lower melting temperatures. It can alter elasticity, so the rock flexes through a passing wave a little differently. It can encourage energy to dissipate, leaving some signals softer and more smeared, as though the planet had exhaled across a pane of glass. And under the right conditions, hydration can also raise electrical conductivity, giving geophysicists another way to test a hidden region besides simply listening to it. This is where the evidence becomes both richer and more delicate. A slower seismic wave does not come with a tidy note attached saying, "caused by water." Hotter rock can also slow a wave. So can partial melt. So can a change in chemistry. A conductive region may suggest hydrogen in minerals, but it may also reflect temperature, interconnected melt, graphite in shallow settings, or other complications. The deep earth is courteous enough to answer, but not courteous enough to answer one question at a time. Scientists work around this by comparing methods, like several doctors listening to the same patient with different instruments. One clue comes from seismic discontinuities, boundaries where wave behavior shifts sharply enough to suggest a mineral transition. In the transition zone, roughly between 410 and 660 kilometers down, those boundaries can move slightly in depth depending on temperature and hydration. Another clue comes from attenuation, the gradual loss of sharpness and strength in seismic energy. Wet or partially molten rock often muffles a signal more than colder, drier material does. Then there is tomography, which sounds grand but behaves in a humble way. It gathers many earthquake paths crisscrossing through the planet, and builds a three-dimensional map of regions that transmit waves faster or slower than average. Tomography is less like opening the earth than like hearing whether a wall is damp by tapping different parts of it. A flat, dry section rings one way, a wet patch gives back a duller note, but so does a crack, so does a hidden stud, so does a pocket filled with something else. The sound is meaningful, just not simple. That is why interpretation matters as much as measurement. To make the picture steadier, researchers often set seismic maps beside magnetotelluric studies. These use natural variations in Earth's electromagnetic field to infer conductivity below the surface. If a region appears seismically unusual and electrically conductive as well, the case for hydration can strengthen. Not become certain, but strengthen. The argument in deep Earth science is often cumulative. No single clue is royal. Several modest clues, if they agree, begin to feel trustworthy. Beneath parts of North America, for example, some studies have pointed to irregular zones in or near the transition zone that may contain hydrated material, perhaps carried downward long ago by subducted slabs. Similar questions appear beneath East Asia, the Western Pacific, and other regions shaped by plate descent. The pattern that emerges is not a neat global ring of uniformly wet mantle. It is messier than that, and more believable for being messy. Some places look comparatively dry. Some look chemically or thermally complicated. Some appear to preserve signatures that make better sense if water-rich minerals survived to great depth before transforming. This patchiness matters. It suggests that the hidden reservoir is not a single smooth shell wrapped evenly about the planet. It behaves more like an uneven archive, with some shelves crowded and others sparse, depending on what kinds of slabs arrived, how cold they stayed, how minerals changed, and whether water was locked in, released, or briefly entered a melt. The deep Earth does not keep one tidy inventory. It keeps a shifting one. That may be the most calming truth in this part of the story. The hidden water is real enough to leave fingerprints in wave speeds, in conductivity, in the depths of mineral boundaries, and in the places where seismic energy seems to tire more quickly than expected. Yet it remains difficult enough to map that certainty arrives in contours, not in bold outlines. Researchers are not tracing a buried sea. They are learning to notice where rock has been chemically altered by water, where it may still be carrying some portion of it, and where the planet's interior sounds just slightly different because of that burden. So by this stage, the claim has changed again. We are no longer asking whether there is an underground ocean waiting in darkness. We are asking where the mantle carries water unevenly, how much is bound there, and how those hidden stores move over immense spans of time. The answer, so far, is gentle and irregular. Deep Earth water appears patchy, dynamic, and still under measurement, more like weather in slow motion than a fixed tank beneath our feet, which leads to the next practical question. If some parts of the mantle are wet and others are not, then the water must arrive by a route. It has to be taken down, piece by piece, from the familiar surface into the dark interior that can only be heard. At the edge of the ocean, the seafloor does something quietly dramatic. It bends. From the deck of a ship, an ocean trench does not look like a doorway. It looks like a place where the map darkens and the numbers become severe. The water above it still moves with wind and moonlight. Waves still rise and collapse in the usual patient way. Yet below that familiar surface, a slab of old seafloor is tilting downward and beginning a journey into the earth. It is tempting to imagine that seawater can only go so far. A little into mud, perhaps, a little into cracks in basalt, then surely the descent must stop. Rock seems, in ordinary life, like the end of the story for water. A puddle soaks into soil, finds a pipe, freezes in a sidewalk seam, but stone itself feels final, dry and closed. The odd truth is that some of the seafloor does not go down empty. Long before an oceanic plate reaches a trench, it has already spent millions of years being altered by contact with water. Near mid-ocean ridges, where new crust is born hot and fractured, seawater seeped downward through cracks and circulates through the upper rock. It reacts with minerals, changes them, and leaves chemical traces of that encounter behind. Faults open more pathways. Cold seawater meets warm interior rock, and the crust is gradually rewritten. Part of that rewriting happens in the mantle rock beneath the crust. There, peridotite can react with water and become serpentinite, a rock whose very name sounds as though it ought to move in slow coils. Serpentinite is not wet in the everyday sense. It does not slosh, but hydrogen becomes bound into its minerals. The rock carries the memory of seawater in chemical form, packed into a structure that can survive pressure and darkness far better than any open crack filled with liquid. So by the time the plate approaches a trench, it is not simply a cold sheet of volcanic rock diving under another plate. It is a layered package shaped by long contact with the ocean above. Sediments ride on top. Altered basalt sits below them. Beneath that, portions of the upper mantle may have been hydrated as well. A listener might picture the whole arrangement as a stone conveyor belt carrying invisible blue cargo. Nothing spills over the sides, nothing glitters in the light, but the cargo is there all the same, sealed into minerals and sent onward by plate tectonics. At the trench, the conveyor begins to descend. As the slab sinks, its pressure and temperature change together. That combination matters. Some hydrous minerals remain stable for a while, like passengers calm enough to stay seated through the first part of the ride. Others do not. Their structures begin to break down. When that happens, the bound water is released through dehydration reactions. This does not mean a neat underground stream suddenly forms and races downward. It means minerals that had been holding hydrogen and oxygen in their structure become unstable and produce fluids or contribute water to melts under new conditions. Much of this release happens before the slab reaches the greatest depths of the mantle. In many subduction zones, water driven out of the slab rises into the hotter mantle wedge above. There it lowers the melting point of surrounding rock, helping to generate magma that may eventually feed volcanic arcs. So a trench and a chain of volcanoes, though far apart on the map, belong to one slow conversation. What goes down in altered oceanic rock can help something else rise again. And yet not all of the cargo is unloaded early. That is one of the most important turns in the deepwater story. If every hydrated mineral gave up its water quickly and completely, the deeper mantle would receive very little from subduction beyond heat, chemistry, and mechanical disturbance. But some materials, depending on temperature, pressure, and the particular path of the slab, can carry water deeper. Cooler slabs are especially interesting because they can preserve hydrous phases longer on the way down. Serpentinite formed near ridges or along great faults in the oceanic plate may descend as part of this package, and other hydrous minerals can continue the transport after earlier ones have broken apart. Subduction, then, is not a simple drain. It is sorting machinery. Some water is shed relatively shallowly and participates in volcanism. Some is passed from one mineral host to another as conditions change. Some may travel onward beyond the depths associated with many volcanic arcs, continuing toward the transition zone where other storage sites become possible. The conveyor belt does not deliver a single parcel to a single address. It distributes cargo along the route, This helps explain why trenches matter far beyond the thin line they draw on a globe. They are not only boundaries between plates, they are intake zones in a planetary circulation system. The visible ocean above sends part of its chemical imprint downward through the moving skin of the Earth. Over immense spans of time, that process replenishes portions of the deep reservoir hidden in minerals below our feet. There is something almost administrative about it. Not dramatic in the cinematic sense, but steady, procedural, and oddly elegant. Ocean water meets young crust. Crust is altered. Minerals are loaded. The plate travels. The trench receives it. Heat and pressure inspect the cargo. Some is released upward. Some is carried deeper. The planet keeps its ledger by moving stone. Seen this way, every trench is both shoreline and doorway. It marks the place where the familiar ocean ends as landscape and begins again as chemistry inside rock. The water does not remain itself in any simple surface sense. It is translated, handed from cracks to minerals, from one depth to another, from cold seafloor into a hotter, slower interior. And as that hidden cargo is squeezed from the descending slab, part of the journey reverses direction. The next chapter follows the water that does not keep sinking, but turns upward instead, toward the long, curved chains of volcanoes above subduction zones. By the time a volcano appears on the horizon, it can seem like the story has become simple again. There is a mountain. There is heat. There is molten rock looking for a way out. After all the buried minerals and descending slabs, this feels almost familiar, like returning from a long underground walk and seeing a chimney at last. But the chimney is not burning on rock alone. It is breathing out water. That sounds backwards at first. Volcanoes belong in the category of fire, ash, smoke, and glowing liquid stone. Water belongs somewhere else entirely, in clouds, kettles, rivers, or the glass beside the bed. Yet one of the quietest truths about volcanic arcs is that water helps make them possible, and then leaves them in great invisible drafts as magma rises toward the open air. A lava subduction zone, a slab of old seafloor descends into the mantle carrying hydrated minerals with it. Much of that water remains bound inside rock for a very long time. As pressure and temperature continue to change, some of those minerals become unstable. They reorganize themselves into new forms that fit the deep environment better, and in the process they release water. Not a cavernful gush, not a hidden sea suddenly uncorked, but a chemical unfastening. Molecule by molecule, hydroxyl leaves one arrangement and becomes available to another. That release matters because dry mantle rock is stubborn. It prefers to stay solid even when it is extremely hot. Add water, and the terms change. Water lowers the melting temperature of the surrounding mantle. Geologists call this flux melting, which is a neat, plain name for a strange event. Rock that would have remained solid begins to melt because a small ingredient has altered the rules. It is a little like adding the right note to a locked chord and finding that the whole thing suddenly resolves. So above the sinking slab, in the wedge of mantle lying between the slab and the overriding plate, water helps generate magma. This is why chains of volcanoes often rise in long curves parallel to ocean trenches. Their position is not random scenery. It reflects a deep exchange underway far below, where released water encourages hot mantle to yield small fractions of melt. Those melts gather, mingle, and begin their patient ascent through a crust that is itself being remade. At depth, magma can hold water within it more easily than it can near the surface. Under high pressure, volatile ingredients remain dissolved in the melt, almost as if the magma is carrying a secret it can keep only while heavily burdened. As it rises, the pressure eases. The secret becomes harder to hold. Water begins to separate from the melt as gas, forming bubbles, films, and pockets that change the magma's behavior. A liquid once comparatively contained becomes more mobile in one sense and more restless in another. This is one reason volcanic systems are not simply molten rock pipes. They are also engines of exhalation. Water vapor is a major volcanic gas. Carbon dioxide and sulfur compounds matter too, of course, but water is often the largest part of what escapes. When magma stalls in reservoirs, intrudes into fractures, or finally erupts, some portion of that deep carried water leaves the melt and joins the atmosphere. The journey that began in altered seafloor and mineral structures ends, at least for a while, as vapor in the sky. Seen this way, an arc volcano is less like a torch and more like a pressure cooker slowly releasing the ocean's ancient breath. The image is not perfect, but it helps. Something has been carried downward, held under severe conditions, transformed, incorporated, heated, and lifted again until release becomes possible. The plume above the crater, so often read only as ash and menace, also contains part of a long planetary circulation system. The sky is receiving material that was once led into the deep earth by plate motion and stored there in stone. This return has consequences far beyond the volcano itself. Water influences how much mantle melts, how sticky or fluid magma becomes, how minerals crystallize, and how continental crust grows over time in subduction settings. It also contributes to the gases available to the atmosphere, where volcanic water vapor can rejoin the familiar surface cycle of condensation, rain, streams, and sea. A raindrop falling on a mountain arc may carry, in a very diluted and ordinary way, the afterlife of a deep process that took millions of years to complete. Even this outward breath is not tidy. Not every molecule sent downward comes back quickly. Some water continues deeper. Some becomes locked again in minerals or trapped in crustal rocks. Some returns through volcanism in geologically brisk pulses. The system is real, but it is not a set of matching pipes with a simple meter at the end. Earth seems to inhale and exhale through different routes, at different speeds, with losses, delays, and long storage in between. That unevenness is part of what makes the story so quietly important. The planet does not merely hide water in the deep and leave it there. It also gives some of it back. From dark mantle wedges to pale volcanic steam, the buried reservoir is connected to air, weather, crust, and the livable skin of the world above. The old viral idea of a secret ocean underground turns out to be wrong in the literal sense, but the real picture is more elegant. Rock passes water inward, heat helps release it, magma carries it upward, and volcanoes return part of it to the sky. And once you notice that exchange, another question arrives almost on tiptoe. If water is always going down in some places and coming back up in others, have those flows balanced across Earth's history? Or has the planet sometimes kept more than it returned? By this point, the water molecule we have been following has become difficult to see. Not because it vanished, but because the scale has changed. We are no longer watching one crack in rock or one bead of melt rising through the mantle. We are looking at the whole planet at once, and the lines that matter now are long, patient arrows, downward at trenches, upward at ridges, arcs, and vents, sideways through minerals that carry their hydrogen like a quiet obligation. The scene is less like weather and more like bookkeeping. On an ordinary evening, the sea can feel permanent in the way a wall feels permanent. The shoreline seems settled. A harbor stays where it is. A familiar beach returns with each season, altered by storms and tides, but recognizably itself. Even across human history, the volume of the ocean can appear to be one of the fixed facts of existence, as if Earth was filled once and has simply remained that way ever since. But the odd truth is that Earth keeps adjusting where its water lies, not quickly enough for a person standing at the coast to notice, not neatly enough for scientists to close every column of the account, yet over millions of years, water is carried downward with oceanic plates, stored for a time in minerals and melts, then returned upward through volcanism, seafloor spreading, and the slow leak of a warm interior. The visible ocean is real, of course, but it is not isolated. It is part of a deeper circulation system whose transactions are written in stone. Geophysicists sometimes talk in terms of reservoirs and fluxes. A reservoir is simply where water resides for a while. Ocean, crust, sediment, mantle minerals, magma, atmosphere. A flux is the rate at which water moves from one reservoir to another. That language can sound dry, which is slightly unfair considering the subject. But it is useful. It lets scientists ask a deceptively simple question. How much water goes down, how much comes back up, and how long does each portion remain where it is? The answers are not tidy. Different trenches carry different amounts of hydrated crust and sediment. Different volcanic systems release different amounts of water. Some descending slabs appear to dehydrate early and feed arc volcanoes above them. Some may carry part of their water much deeper, past the regions where melting is easiest. At mid-ocean ridges, freshly formed crust releases water as hot mantle rises and melts. Elsewhere, hydrothermal systems trade water between rock and sea in ways that complicate the count, so the planetary ledger is not a neat household notebook. It is more like a slow savings account managed by moving continents, with deposits and withdrawals entered in several handwritings at once. At trenches, water is deposited inward. Oceanic crust and sediments arrive already altered by their contact with seawater. Minerals formed or transformed near the seafloor carry hydroxyl into the subduction system. As the slab descends, some of that bound water is released. Some contributes to melting in the mantle wedge, helping to generate magmas that eventually return water toward the surface. Some may remain stored deeper in stable mineral phases, adding to the mantle's hidden inventory. At volcanoes and ridges, water is withdrawn from the deep account and returned to shallower circulation. It can emerge dramatically from erupting magma, or more quietly through persistent degassing, hot springs, and submarine systems that never attract much public attention. The planet does not issue one grand receipt. It exhales through many small openings as well as a few famous ones. When researchers estimate these exchanges, they often arrive at values on the order of hundreds of millions to perhaps a few billion kilograms of water moved each year along major pathways. The exact figures vary by method and by assumption. Trench input estimates depend on how hydrated the incoming plate truly is and to what depth. Volcanic output estimates depend on how much gas escapes visibly, how much escapes diffusely, and how representative any one volcanic arc really is. The numbers are useful, but they do not click together like machine parts. That uncertainty is not a failure. It is part of the science. Earth is not offering its accounts in a clean spreadsheet. Scientists are reconstructing them from seismic images, rock chemistry, laboratory experiments, melt inclusions, isotope studies, and careful measurements of gases rising from remote vents. The remarkable fact is not that the numbers remain debated. The remarkable fact is that the debate exists at all because the flows are real enough to measure, and those flows matter beyond the question of where water happens to be stored. Water changes rock behavior. A more hydrated mantle can become weaker and less viscous. Water lowers melting temperatures in some settings, helping magma form where dry rock would remain stubbornly solid. Melting and hydration can influence how easily plates bend, sink, and interact. In other words, the ledger is not just recording planetary behavior. It helps shape it. Over immense stretches of time, even modest imbalances could matter. If deep Earth stores water more efficiently during one era, the surface system may gradually adjust. If more water is returned upward than carried down, sea level and continental environments may feel the difference eventually, not as a sudden event, but as a long rearrangement of boundaries. Shorelines migrate. Inland seas appear and vanish. Climates respond indirectly to tectonic changes that began far below any cloud. This is one reason the coast can look so calm while participating in something so mobile. The apparent permanence of the ocean is maintained by exchange. Stability, in this case, is not stillness. It is balance achieved through motion so slow that no eye can watch it directly. And perhaps that is the gentlest surprise in the whole hidden water story. The sea beside us is not only rain collected in basins. It is also the surface expression of a planet keeping accounts across depths and ages, receiving water into hot descending rock, releasing it again through fire and fracture, and never quite letting the books stand still. Long before there were familiar beaches, however, this ledger had already begun to open. If the last chapter left us with water moving in and out of the deep earth like a patient exchange, this one asks a quieter and older question. Before water could cycle, before there were trenches, clouds, or even stable oceans, where did any of it come from at all? It is tempting to give the story a single elegant beginning. One can imagine a dry young earth sitting under a violent sky, waiting for icy messengers from the outer solar system to arrive and donate the future oceans. For many people, this is still the default picture. Water seems like something delicate and imported, something that must have come from colder, safer neighborhoods far from the sun. But the odd turn is that Earth's water does not behave like a gift with one return address neatly attached. The evidence points instead to a mixed family history. Some water likely arrived in the rocky materials that built the planet in the first place. Some may have been added during later impacts. Some hydrogen may have been present early enough to enter minerals, melts, and the growing interior before the surface had finished becoming itself. To picture the setting, it helps to forget the calm globe we know. The young Earth was not blue and white. It was assembling from dust, metal, stone, and repeated collisions. Heat came from impact after impact, from compression, and from radioactive decay. Much of the outer planet may have spent long periods as magma ocean rather than crust in the ordinary sense. In that brightness, it is easy to assume that any water would simply vanish, and some of it certainly did. Steam atmospheres can be stripped, light gases can escape. Giant impacts can erase local histories with alarming efficiency, yet disappearance is not the whole story. Water is awkwardly persistent when chemistry gives it places to hide. Not always as liquid, and not always as a cloud, but as hydrogen bound into minerals, dissolved into melts, and folded into the hot interior while the planet was still sorting itself into core, mantle, and crust. So the early Earth may have been both violent enough to lose water and chemically accommodating enough to keep some. Scientists try to reconstruct this beginning the way a genealogist studies several faint signatures on old paper. No single name tells the whole lineage. Instead, researchers compare ratios, especially the ratio between ordinary hydrogen and its heavier sibling, deuterium. Ocean water has one signature. Different meteorites have others. Comets vary. Samples thought to reflect parts of the mantle add another clue, though even those are filtered through long planetary history before they reach us. For a while, comets seemed like appealing donors because they are visibly icy and dramatic. But many measured comets carry hydrogen signatures that do not match Earth's ocean water especially well. Some are much richer in deuterium. That does not banish comets from the story entirely, but it makes them less convincing as the sole source. Certain classes of meteorites, especially carbon-rich chondrites, often look more compatible. They come from bodies that are rocky, primitive, and capable of carrying water-bearing minerals into the inner solar system. In other words, some of the ingredients of Earth might not have been truly dry to begin with. That matters because accretion is not just delivery. It is incorporation. If a growing planet is built partly from water-bearing material, then water is not simply sprinkled onto the finished surface like a late garnish. It can become part of the architecture while the walls are still going up. Some fraction may be released upward during melting and degassing. Some fraction may remain below, retained in the mantle through processes that began astonishingly early. This is where the hidden interior reservoir complicates the old question in a useful way. If part of Earth's deep water descends from ancient material trapped during formation, then the mantle is not merely a modern storage space. It may also be an archive, not a perfect one, because billions of years of mixing, melting, and recycling blow the record, but an archive all the same. The water moving through the deep Earth today may contain a portion of a much older inheritance than the surface alone can easily display. There is also the matter of timing. The classic image of a completely dry Earth later rescued by external ice now looks too simple. A more realistic picture is layered. Early accretion may have supplied water-bearing minerals. Large impacts may have both added and removed volatiles. Magma oceans may have released thick steam atmospheres. Some of that atmosphere may have escaped to space, while some later condensed as the planet cooled. Meanwhile, the interior retained part of the budget, sheltered not by calm conditions, but by chemistry and pressure. So when we ask where Earth's first water came from, the answer may be less like naming one parent and more like tracing a family through several households. There are chondritic relatives, perhaps a cometary visitor or two, deep interior witnesses, and surface records rewritten many times. Each keeps only part of the surname. Together they suggest that the water beside us is both immigrant and native, both delivered and inherited. That mixed origin feels strangely fitting for this planet. Earth is rarely most interesting when it offers a clean boundary. Land trades with sea. Surface trades with mantle. Loss and retention happen at once. Even the oldest water may not belong entirely to one realm or one moment of arrival. And perhaps that is the gentlest surprise in the story. The water in a glass on the bedside table does not need a single dramatic entrance to be remarkable. It may carry pieces of several beginnings: dust from the early solar system, chemistry from a molten Earth, and a deep planetary memory stored far below the places where oceans shine. In the next chapter, the question shifts from origin to endurance. However Earth's water first arrived, or formed part of the planet from the start, the greater miracle may be that Earth managed to keep enough of it for so very long. By this point in the journey, the hidden water inside Earth no longer feels like an odd mineral detail. It begins to look like part of the reason the familiar world above us has remained familiar at all. A shoreline seems to belong to the surface. Rain, waves, estuaries, and mist all perform in the open air. Yet the longer scientists study the planet, the harder it becomes to separate that visible performance from the quiet storage room far below. When we picture a habitable world, the usual instinct is to look upward. We ask whether a planet sits at the proper distance from its star, where heat is gentle enough for liquid water to survive. That is a sensible beginning. Too much sunlight and water escapes or boils away. Too little, and oceans freeze into a long stillness. But distance from a star is only the front door. What matters after that is whether a planet can keep water moving, trade it between reservoirs, and avoid spending it all in one place at one time. Early Earth had to solve exactly that problem. The young sun was fainter than it is now, and yet the geological record suggests that dark oceans still gathered and endured. Continents were smaller, the atmosphere was different, and the deep interior was hotter. Nothing about the setting was truly settled. And still, over immense spans of time, the surface did not simply lock all its water away or lose it altogether. Some of the explanation may lie in the slow exchange between the ocean we know and the water hidden in hot rock below. This is where the deep reservoir becomes less like a curiosity and more like a partner. Not a dramatic controller pulling levers, and not a secret sea waiting to be discovered, but a patient backstage system. On the visible stage, oceans spread, clouds gather, rivers cut valleys, and life learns the habits of coasts and tides. Behind the curtain, plate tectonics carries water downward in altered crust and minerals. Heat and pressure reorganize those materials. Some water returns upward through melting and volcanism. Some remains bound deeper within the mantle. Over long intervals, the planet keeps adjusting the balance. That balance matters because surface water is tied to climate, and climate is tied to rock. When continents rise above sea level, rain and carbon dioxide interact with silicate minerals in a process known as weathering. It is a remarkably untheatrical piece of planetary chemistry. Raindrops fall, rock slowly changes, dissolved materials travel to the sea, and carbon is gradually locked away. Yet this quiet process helps moderate climate over millions of years. Too warm and weathering can increase. Too cool and it can slow. For that thermostat to function, there must be exposed land, active geology, and a long-term way to cycle materials through the crust and mantle. Water is involved in every part of that arrangement. It helps rocks melt more easily in some settings. It weakens minerals, changes how the mantle flows, and influences tectonic motion. It helps build continental crust, which then becomes the stage on which weathering can operate. In that sense, a planet's hidden water does not merely sit in reserve. It participates in the architecture of habitability. The chemistry of a crystal lattice, far below any root or coral reef, may be part of the reason forests and reefs have had a stable home. The contrast with our neighboring worlds makes this easier to feel. Venus is close in size to Earth, and for that reason it often appears in planetary science as an uncomfortable mirror. But whatever water Venus once had, the modern planet is astonishingly dry at the surface, wrapped in a crushing atmosphere and extreme heat. Researchers still debate the exact sequence of events, but Venus seems to have lost the kind of coupled ocean interior system that Earth preserved. Mars offers a different sadness. Its ancient valleys and minerals tell us that water once moved across its surface, yet the small planet cooled, its geology quieted, much of its atmosphere thinned, and the long conversation between interior and ocean was diminished. These comparisons do not prove that Earth's deep water reservoir alone saved the biosphere. Planets are too complicated for a single heroic explanation. Size matters, magnetic shielding matters, atmospheres matter, impacts matter, the history of a star matters. Even so, Earth keeps suggesting a broader lesson. Habitability may depend not only on having water, but on having a planet able to manage water over deep time. Too much stranded at the surface, and continents may drown beneath global oceans with limited exposed rock for weathering. Too much lost upward or outward, and the surface dries into silence. Too much locked away without return, and the cycle stalls from the other direction. That possibility now shapes how scientists think about distant worlds as well. Some exoplanets may be rich in water, perhaps far richer than Earth, but abundance alone does not guarantee a comfortable shore. A world wrapped in very deep oceans with little exposed land might behave quite differently from our own. Another planet might keep water mostly inside, or mostly above, or lose the exchange entirely. We are only beginning to understand these possibilities, but the old picture of habitability as a simple line around a star has already become gentler and stranger. A living world may need an unseen conversation between surface and depth, so the hidden reservoir beneath our feet becomes part of a biological story without ever containing a fish or wave. It is part of why shorelines could remain shorelines, why climate could wander without permanently breaking, why continents could rise and weather, and why the thin skin of water at the top of the planet could persist long enough for cells, forests, animals, and eventually people to notice the sea. It is a humbling thought, and also a calming one. Every living coast may rest in some quiet sense on decisions made hundreds of kilometers down, in dark minerals under enormous pressure, where water is held so discreetly that the planet can seem dry even while carrying a hidden reserve. And after traveling outward to compare Earth with Venus, Mars, and distant worlds, we can return to something smaller again. One patient molecule, still moving through our own planet, still passing between stone and sea. If you like, you can return now to the simple glass of water beside the bed. It has been waiting there all along, looking almost too ordinary to deserve this much thought. A clear drink, a small weight in the hand, a surface that trembles slightly when the room shifts or the floor settles. We are trained to think of water in familiar neighborhoods. It belongs in cups, in sinks, in clouds, in rivers, in the sea. Rock belongs somewhere else entirely. Rock is the opposite of water, or so it seems, dry, fixed, stern, uninterested. And yet the quiet oddity we have been following is that these two worlds were never truly separate. The water you know at the surface and the water hidden far below are not members of rival realms. They are part of one long circulation, one planetary habit, moving at more than one speed at once. A raindrop falls in minutes. A river works over months. A glacier takes centuries to change its mind. But the deeper exchange unfolds so slowly that it almost slips outside ordinary feeling. A single passage inward and outward can take millions of years. By human standards, that is less a journey than a condition of the world. So imagine, very gently, one tiny portion of the water in that glass beginning elsewhere. Perhaps it falls first as rain onto dark volcanic rock or old seafloor sediment. Perhaps it seeps downward through cracks, reacting as it goes, becoming part of minerals in the oceanic crust. It is no longer a bead or a droplet in any familiar sense. Its hydrogen and oxygen have entered new arrangements. The water is being carried not in a pocket, but in structure, held in the disciplined architecture of stone. That piece of crust drifts, as oceanic crust always does. It moves away, cools, thickens, gathers sediments, and after a very long interval approaches a trench. There, the descending plate begins its long inward passage. Pressure rises, temperature rises. Minerals that were comfortable near the surface become less comfortable in the deep. Some release water earlier. Some carry it farther down. A portion may enter minerals able to keep hydroxyl hidden in their atomic patterns under immense pressure, deep within the mantle's busy interior. Nothing about this is hurried. The scale of the process is so large that urgency would be the wrong emotion. Earth is not gulping and exhaling in the manner of an animal. It is breathing through stone, and one breath lasts longer than whole branches of life have existed. That is perhaps the gentlest useful metaphor to keep. Not lungs exactly, not a heartbeat. Something slower and more patient. At trenches, the planet draws water-bearing material inward. In the mantle, heat and pressure rearrange what can be carried, what must be released, what becomes part of mineral structure, and what helps rock begin to melt. In other places, through magma and volcanism, some of that water returns upward, enters the air, condenses into cloud, falls again as rain, and eventually finds its way back to streams, soils, aquifers, ice, and sea. Along the way, science catches glimpses rather than a complete panoramic view. A diamond may preserve a mineral inclusion from great depth. A laboratory press may reproduce punishing conditions inside a chamber small enough to fit in a room. Seismic waves may arrive slightly changed after crossing regions where minerals behave as though water has altered them. Volcanic gases and magmas may hint at material that has been traveling upward from depths no person will ever visit. None of these methods gives a perfect map. Together, they act more like overlapping lanterns in a very large dark house. That partial light is enough to change the story. The old viral image of a hidden ocean beneath our feet turns out to be wrong in the literal sense, and still strangely useful in the emotional one. It is wrong because there is no underground sea sloshing beneath the crust, no giant chamber with waves rolling in the dark. But it points clumsily toward a truth that is harder to picture and in some ways more beautiful. Water can be present where it does not look like water at all, stitched into minerals, released by transformation, borrowed by melt, returned by fire, and sent back into weather, which means the glass beside the bed is not merely local. It is local in the practical sense. You could lift it now, you could drink it. It could quench thirst in a moment, but it is also the nearby expression of an ancient circulation. Some of its atoms may have spent part of their history in cloud, part in snow, part in ocean, part in poor spaces underground, and perhaps at some remote time part in rock descending into the mantle or rising back out through magma and gas. Not every molecule follows that deep path. Many never do. But the possibility itself enlarges the room. The familiar water in ordinary life is connected, however unevenly and over staggering spans of time, to the hidden water held within Earth's mineral interior. The surface ocean and the deep planet are not strangers exchanging occasional messages. They are parts of one system that has been negotiating with itself for eons, shifting water between visibility and concealment, between sky and stone. And so the final feeling is not that the world beneath us is secretive in a dramatic way. It is secretive in a calm way. It keeps its water not in theatrical caverns, but in the quiet discipline of matter itself. Locked, released, carried, transformed, and carried again. Beneath the stillness of the night, beneath coastlines and plains and sleeping cities, that circulation continues. The planet keeps breathing through rock. The dark interior keeps some part of the surface world in safekeeping, and above it, on the thin blue skin we know best, a glass of water waits in the lamplight, simple as ever, while the deeper story recedes softly into the dark.